Hey friends, welcome. Today we will be discussing one of the solutions of the Schrodinger wave equation, and that is the particle in one dimension box. So this represents the translation motion of any macroscopic particle along a single axis, that is we can take either x-axis, we can take y-axis, or we can also take z-axis. And in this lecture we will be obtaining the value of the energy of the particle that is confined in the one dimension box. We will be obtaining the wave function for the particle which is confined in one dimension box. We will also look into the normalized wave function. Also we will be looking at the plots of wave function versus a position, and we will be looking at the plot of population and density versus the position also. So these are the main topics that we will be discussing in today's lecture. Let us consider that we have a free particle, and this free particle basically it is moving in any particular direction. Yeah, in any, suppose it is moving along x-axis and it is performing a translation motion. Now in order to confine this particular particle, we are considering that we are considering that our particle is confined between the two walls, such that the distance, that is this is at initial position x is equal to 0, and suppose this is a, so the total length of the box is a. Okay, so over here the value of the x will lie between 0 to a. As we all know that the particle is confined in this wall and the particle is performing motion, we know that any particular system under motion will possess kinetic energy, and hence we are considering that the potential energy of this particular particle inside the box is 0, and for consideration we are considering that the potential energy outside the box is considered to be infinite. So we have two conditions to solve. First will be when v is at infinity and v is potential energy at 0. So we will be using Schrodinger wave equation, and basically as it is particle in one dimension box, we will be using one dimension Schrodinger wave equation, and one dimension Schrodinger wave equation will be represented by d square psi by dx square plus 8 pi square m by h square. We could write this as h cut square also, so in numerator we will have only 2m into e minus v psi, and that is equal to 0. So this is our Schrodinger wave equation for one dimension. Now for the first condition, if we are considering if we are considering v equal to infinity, then for potential energy equal to infinity, we will have d square psi by dx square plus 8 pi square h square e minus infinity into psi, and that will be equal to 0. So over here the value of energy will be very less as compared to infinity. Also when we multiply all these terms with infinity, we will get infinity. So our expression would be d square psi by dx square minus infinite psi, and that will be equal to 0. And when we solve it, we will get psi will be equal to 0. So we could take this on that right hand side. Infinity, we know it is 1 upon 0, so 0 will be on right hand side, and hence we will have, or we will get psi is equal to 0. So for psi is equal to 0, that literally means that no particle exists outside the wall. All the particles will exist inside the box, and this is the forbidden region, or this is, we can refer it as a classically forbidden region for the particles to exist, or the probability of finding the microscopic particles in this classically class in this region is classically forbidden. Now for V is equal to 0, if for inside the box the potential energy V will be equal to 0, and hence the Schrodinger wave equation will take the form d square psi by dx square plus 8 pi square m by h square into E minus V, and V is 0, so that will be equal to 0 into psi, and that will be equal to 0. So we will be left with d square psi by dx square plus 8 pi square m h square E into psi, and that is equal to 0. Now I could take all these terms equal to a constant, that is k square. So I could write capital K square is equal to 8 pi square m by h square, 8 pi square m E by h square. So this is k square, and I will substitute k square in this expression. So we will have d square psi by dx square plus k square psi, and this is equal to 0. Now this is a second order differential equation, and there are several solutions for the second order differential equations. Okay, we are interested in the solution which is most suited to us, and hence the solution, that is psi is equal to a sin kx plus b cos kx. So this will be the solution that we'll be using for the solution of a particle in one dimension box. Now we need to find the values of this constant, and when we obtain the values of this constant, we will get the value of the wave function. Okay, so in order to find the values of constant, we will be using the boundary conditions, and for the boundary condition we know that the value of wave function on the walls, the value of wave function on the walls as well as outside the walls will be 0, and similarly the value of potential energy also on the wall as well as outside the wall will be infinity. So for psi is equal to 0, at we will have x will be equal to 0. So when we substitute this, so psi will be equal to 0 at x is equal to 0 and x is equal to a. So we will be using both these conditions one by one. So this is our first boundary condition, and hence we will have for first boundary condition x is equal to 0, psi will be equal to 0, and hence we will have 0 will be equal to a sin k into 0 plus b cos k into 0, and sine of 0 we know it is 0, and cos of 0 it is 1. So we will have 0 is equal to b. So the value of b is 0, and hence the second term, that is cos term, will disappear from the expression, and hence we will only have the wave function psi is equal to a sin kx. Okay, now looking at the second boundary condition, at second boundary condition we will have for x is equal to a, psi again will be equal to 0. So now this is our wave function, and we will have 0 is equal to a sin ka. Okay, now over here a is a constant, and this a cannot be equal to 0. So a is not equal to 0. So obviously to make this expression or multiplication of both these terms equal to 0, sin ka will be equal to 0, and for that we know that sin ka is equal to 0, and sin ka will be equal to 0 when we have sin n pi, that is when n is equal to 1 2 3 4 and so on. Then sine of pi is equal to 0. So sin ka will be equal to sin n pi, and hence we could write ka will be equal to n pi. So the value of k that we are getting is n pi by a. So this is the value of the constant k, and hence our wave function will be psi is equal to a sine n pi by a. Okay, so this is the value of our wave function for a particle which is confined in one dimension box, but this value is an unnormalized value, and we all know that in quantum mechanics all the wave functions that we are using are normalized wave function. And why it is unnormalized? Because we have a constant a over here. So in order to obtain the value of, or in order to normalize this wave function, or we need to normalize this wave function, and in order to normalize it, we know the condition for normalization, that is integration psi into psi star dx, and when this is equal to 1, then the wave function is normalized one. So we could substitute this wave function or value of this wave function in this expression, where psi is the wave function and psi star is its complex conjugate. So over here psi star will also have the same value. So for normalization we will have a sine n pi by a into, yeah, so when we substitute n pi by a we have x also. So I have just forgotten x over here. So we will have n pi x by a, and similarly we have sine n pi x by a into dx, and that will be equal to 1. So this will be a square sine square n pi x by a into dx, and that is equal to 1. Now we all know that sine square theta is 1 minus cos 2 theta by 2, and also integration of cos ax dx will be sine ax by a. So by using both these formulas we can solve this expression, and a over here is constant, so a square by this 2 I am taking it out, so 2 into integration 1 minus, and the limit of integration will be between 0 to a. Okay, limit of integration will be between 0 to a, because that is the length of the box. So we will have 1 minus cos 2n pi by a into dx, and that is equal to 1. So when we integrate it we will have a square by 2 into so integration of dx will be x, and that will be x between the limit 0 to a minus, we will integration of cos 2n pi x by a will be again a by 2n pi, that is this a, into sine of 2n pi by a, and the limit is between 0 to, okay, so this will be the values. Now further, when we substitute upper limit minus lower limit, then a will be cancelled out, and sine of 2n pi or sine of pi, that is 0, and when we substitute the lower limit, this will be x, okay. So when we substitute the lower limit this will be 0, and when we substitute the upper limit also this will be 0. So the whole term will go away, and this will be a, and this is equal to 1. So hence we will have a square by 2 into a, and that is equal to 1. A square will be equal to 2 by a, and a is equal to under root 2 by a. So this is the value of the constant a, and hence the value of the normalized wave function for the particle that is confined in one dimension box is under root 2 by a sine n pi x by a. So this is the value of the normalized wave function. Okay, now we have obtained the normalized wave function. The next thing we will be obtaining is the energy, and in order to obtain the energy we have two expressions. First is k is equal to n pi a. Also we have considered k square is equal to 8 pi square me by x square. So I will just write down both the expressions. So we have written k square is equal to, so these are the two expressions, and hence we could equate both this, and we will have 8 pi square me by h square is equal to n square pi square by a square. So pi square will be cancelled out, and we could rearrange this expression in the form of energy. So the energy E is equal to n square h square upon 8 m a square. So this is the expression for the energy of the particle which is confined in the one dimension box, and over here the values of n will lie from 1 to 3 and up to infinity. So for n is equal to 1, the value of E is h square upon 8 m a square, and this value is known as the 0 point energy, that is the minimum energy that a system will have, and that is the 0 point energy. The value of 0 point energy is not 0, but it has certain value, as we know that the particles are under continuous motion, and as a result they will possess certain amount of energy. So this is the value of the 0 point energy, the lowest energy. For the first excited state n will be equal to 2, and hence the value of energy will be 4 h square upon 8 m a square. Similarly for n is equal to 3, 4, 5 and so on. So we will in general we will get h square 8 m a square. I will write it as x. So for n is equal to 1, e will be equal to 1x. For n is equal to 2, e will be equal to 4x. For n is equal to 3, e will be equal to 9x. For n is equal to 4, e will be equal to 16x and so on. Okay, so this shows that the energy levels, they are quantized. Now the next point is the plot of wave function and the population density versus the position. And over here, for in this plot we will have 3 points. We will have a maxima, we will have a minima. Maxima is the point on x at which the value of wave function psi is maximum. Minima is the point at which the value of wave function is minimum, and the third point that we'll be having is a node. So node is the point at which the wave function or the value of wave function is 0, and except boundary condition along the x-axis, along the whole length, the point where the wave function is 0 is referred as node. Okay, so for ground state, that is for n is equal to 1, the wave function psi, we know it will be under root 2 by a sine, we will have pi x by a, as we have substituted n is equal to 1. Now in order to find maxima, psi maxima will be equal to under root 2 by a, and hence we will have sine of pi x by a, this should be equal to 1, and sine of 1, that is sine we have for sine pi by 2, the value is 1. Okay, so hence we will have pi x by a, that is equal to pi by 2, pi cancel, and we will have x equal to a by 2. So the maxima for n is equal to 1 is at when the value of x is half of the length of the box. So when we draw, or suppose this is the length x 0 to a, then this will be our a by 2 point, and maxima will be, this will be our maxima. Okay, and over here we won't have any minima, and node also over here we won't have any node over here in this particular for n is equal to 1. For second excited state, third excited state, we could solve in the similar manner, and we will get the plot in this particular manner, that is for, this is for n is equal to 1, the energy is h square upon 8m a square. Similarly for n is equal to 2, we will get two maxima, sorry, one maxima, one minima, and one node. So this will be at a by 2, and this will be at a by 4, and this will be at a by 2. Similarly for 2 3, we will have one maxima, sorry, two maxima, one minima, and we will get two nodes, and the energy will be 9 h square upon 8m square. Okay, so this is the value, or these are the plots for the wave function psi. And similarly for the wave function that is for population density psi 1, we will have the same plot. Population density will have the same plot. Let me use red. For psi 2 square, this will be square, we will have, the graph will have this behavior, that is 1, and then again it will show the maxima, there won't be any minima. So this is our node. For psi 3 square, we will have 1, then 2, and then 3. Okay, so in this way we will obtain the graph of the wave function and the probability of finding the particle at any particular point, because we know that the probability psi square is the probability, and the value of probability is always positive, and hence it is coming on the same side. And over here the number of nodes will always be for nth energy level. For nth energy level, the number of nodes will be always n minus 1. For nth energy level, the number of nodes will be always 1 less than on the energy level. So this is the how we represent the graph. So hence in today's lecture we have seen the normalized wave function for the particle that is confined in one dimension box, that is under root a by 2 sine n pi x by a, and we have also seen the energy, that is n square x square upon 8 m a square. So hope the derivation is clear. Thank you very much.